Hi, I am Abhinay Kumar. I am a master's student at Indian Institute of Technology, Jodhpur, and we are at Helicopter Lab in the mechanical department in this college. We are working on design of indigenous autopilot system for aerial vehicles, and our aerial vehicles are basically for multi-rotors and helicopter configuration of mini size. And this is the system that we are developing. We are developing the hardware and the software architecture as well. We are taking off-the-shelf components from the market and we are integrating them with the microcontrollers, and we are writing all the firmwares, drivers, controllers, estimation and control algorithm. And ultimately we are driving these actuators to stabilize this platform in the mid of the air and to take the vehicle from A point to B point in autonomous mode. So the vehicle's autopilot, that is the avionics system of the vehicle, consists of various sensors, the motor drivers, the actuators and the communication modules. The sensors consist of the navigation sensors that have the inertial sensors as well as GPS, LiDARs. The inertial sensor consists of accelerometer, gyroscope and magnetometer. And the navigation sensors consist of the GPS, LiDARs and the barometer. And all the sensors are fused with each other using the proper estimation algorithm to get the proper estimate of the vehicle. And all the sensors are mounted on board on a pad that is subsequently mounted on the dampers to damp the vibration that is coming from the rotors. So all the algorithms, that is from stabilization algorithm and the navigation algorithm, are running on board. So prior to the flight we do the rig test and stabilize the vehicle in the rig, and this is the rig in which the angle control is stabilized. And right now the vehicle is mounted along the roll axis, and the vehicle will try to stabilize along the roll axis that will show in the later section of the video. Similarly, once the roll and pitch is stabilized in this axis, then we mount the vehicle on that platform and it will try to stabilize the vehicle along the yaw axis. Once this stabilization is achieved, then we fly the vehicle in indoor environment without changing any gains. We subsequently change the parameters of the control so that it can stabilize the vehicle in the changing dynamic environment. And once this tuning is done from a rig in the indoor environment in the air, then we take the vehicle outside in the outside environment, then try to fly the vehicle in hover configuration. And right now we have achieved all the stability from rig to the indoor environment to the outdoor environment, and the vehicle can hover without any pilot interventions for a very long time until the battery is discharged. And the vehicle is also capable of going from A point to B point without any intervention. The pilot just have to give the final location using the GPS coordinates, and the vehicle will try to follow that coordinates. And prior to the development of all the firmwares, we have to study the dynamics of the vehicle. For that, the proper estimation of inflow and what are the rotor loads generated on the vehicle, we have to do a separate study for that. So to study one rotor, how the loads are generated along all the three axes, that means how the forces and moments are varying when the vehicle is moving in the dynamic environment. For that, we have designed a study and the test rig that she will be explaining, on which she will be explaining how the loads are varying along all the axes during the flight.
Hello, my name is Bhanumati CV. So, to design the control system of multi-rotor or rotary wing vehicle, we have to do the dynamic modeling, and for that we require rotor loads, and for that we have designed this experiment in which the rotor is oscillating as well as rotating. So the experimental setup have the flexibility to oscillate the platform at different frequency, and the rotor can also rotate at different RPMs. We are using an encoder to measure the angle, and we are using force sensor to collect the forces and the moment in all three directions. Data collected from the force sensor will help us to get the better estimate of the inflow and the rotor loads.
So the vehicle consists of the avionics system that is mounted on the vehicle, on the top of the vehicle. And the avionics system consists of the microcontrollers, the inertial sensors and the navigation sensors. Inertial sensors have the accelerometer, gyroscope and magnetometer mounted with it, connected with it. And the navigation sensors consist of the GPS, the LiDARs and the sonar. And it also have the health monitoring system for monitoring the health of the battery states. That gives you visual and audio signals when the battery voltage go below a certain level. And then all the programs and the drivers that are running on the microcontroller interface with all the sensors and do the calculations and command the motors using these motor drivers to rotate at a particular RPM, and that rotation speed is given to all the motors so that the vehicle can stabilize in the middle of the air and can complete whatever the task that is given to the vehicle. And so this is the primary task, primary board that we are developing. Right now this board is for the multi-rotor vehicle, and then we are trying to implement the same on the helicopter that is kept beside me. So this is the board that we are developing, and it consists of all the inertial and navigation sensors. Inertial sensor consists of the accelerometer, gyroscope and magnetometer, and the navigation sensor consists of the GPS. The GPS is mounted in this box that is mounted above one post, and the other sensors also consist of the LIDARs that are mounted here and the sonar. So both the sensors works in indoor and outdoor environment. This works up to 6 meters, this works up to 12 meters. And this is the health monitoring system of the vehicle. It consists of the audio and visual feedback when the battery voltage go below certain level. And all the programs that are running in this microcontroller that are running on board the vehicle. And this board can stabilize the multi-rotor vehicle that is in quad-rotor configuration. And then later we are planning to use the same board to fly the helicopter that we have also procured. And so this is the system that we are developing now. Right now we are stabilizing the vehicle along the roll axis. This test is necessary prior to the flight so that we can test whether the vehicle is stable along its axis or not. So when the pilot gives input along one of the direction along the roll axis, then the vehicle have to follow the command. So when the pilot doesn't give any input, then the vehicle will be in horizontal configuration, and when the pilot gives any input, the vehicle will tilt to the side corresponding to the stick input. So right now we can see that the vehicle can follow the stick input that is given by the pilot, and when the input is not given, the vehicle will come back to its original position.